Hello everyone. Thanks for joining today. This is another webinar based on the series for basics of viscosity that we started last year. And today, as Grace mentioned, we're going to talk about different types of viscosity and how to measure them. So before we start, I want to show you, this is our team of superheroes. So if you guys have any questions after the webinar and all the materials that we're sharing today will be available on our website shortly. If you have any questions, you can ask to either of us regarding our instruments or viscosity measurements in general, or some specifics about measuring your samples or anything that you can imagine. So with that, I would like to get started. So we're going to cover different types of viscosity and how to measure them. But first, I would like to start with what is viscosity? And we often define it as the resistance of a fluid to flow. But in today's presentation, I think it makes sense to focus a little bit more on what is going to be the type of flow, because that's going to determine what type of viscosity you're going to be measuring. So if you are for example, sharing a fluid between two plates, that's going to be shear flow, so you're going to be measuring shear viscosity. If you are pushing a fluid through a piston, you're going to have a different type of shear flow, but that's going to be also shear viscosity, so that's going to be the property that you're going to be looking into. If you are injecting or injecting, for example, ink through a nozzle where you have a constriction of the flow, then you're going to have a combination of both shear and extensional viscosity. And all these types of viscosity that are related to flow are just simplifications of what actually happens on real flows that allows us to measure real properties. So as is simplified here, you can have different resistance to flow or different viscosities. People often refer to it as the thickness of the fluid. And if you have something with very low viscosity, like water, you're going to require lesser forces to make the fluid flow. On the other hand, if you have something that is very high viscosity, like honey, you're going to require a much larger flow to make fluid flow. So within the field of rheology and the study of flow of matter and material properties, we're going to be covering viscosity and then different types of viscosity. We're going to cover two main types depending on the type of flow, shear and extensional. And most applications can be covered by either individually by each of those or combinations of these two types of viscosity. And then within shear viscosity, we're going to look at some definitions like dynamic, kinematic, and how those compare to each other, and then the difference between different degrees of measurements, such as absolute, apparent, and index viscosity measurements. And then as a side application, we're going to look at intrinsic viscosity, which is related to shear viscosity, but it's a property on its own. And we're going to be covering questions such as, what is X viscosity? What are the applications for this type of viscosity? How can it be measured? And how do we measure it at RheoSense? So without further delay, I'm going to start with shear viscosity. So as you could imagine, or what I just said, shear viscosity is the resistance of a fluid to shear flow or shear stresses. So you can imagine that if you have fluid contained between two parallel plates, and you just highlighting here a part of that fluid, if you start displacing the upper plate at a velocity v1, then to overcome the shear forces that are exerted by the fluid or the fluid's resistance to flow, you're going to need a force. And this is what's going to happen. Your fluid is going to get sheared in between those two plates. So you can define the shear stress as the ratio of that force that you need to exert into the upper plate divided by the area of the plate. and you can define the shear rate as the ratio of the velocity, the steady state velocity, divided by the distance between the two plates. And then shear viscosity is defined as the ratio of those two, shear stress to shear rate. Now, in many cases, it's very common for shear viscosity, which is the most common kind of measured viscosity. It's very common and very often we drop the shear. So when we talk just about viscosity, we are often referring to shear viscosity. So now within shear viscosity, we have a few different types. We have dynamic viscosity, which is natural measurement of the resistance of a fluid to flow, and is the definition that I just gave on the previous slide. We also have kinematic viscosity, which is, you can think of it as a momentum diffusivity or a measurement of the propagation of momentum by friction. So those two are very easily related just by density, as you can see here. So the difference is that kinematic viscosity, it's a derived property and is density dependent, while dynamic viscosity is a fundamental or more basic property. Some of the differences are also related to the units. Of course, they have different units. For dynamic viscosity, we often use millipascal seconds or centipoise, which are equivalent. And then for kinematic viscosity, you have diffusivity units, so you have centimeter squares by second or centistokes. So you want to look at applications that look at the interactions between molecules, the force or the energy required to exert some kind of flow or subject some sample to some specific flow. Then you're probably going to be looking at dynamic viscosity. If you're just interested about the fluid motion and the velocity field, as in Navier-Stokes equations, then you will probably be using kinematic viscosity. There is also some differences in how do we measure these two related properties. And I give a few examples here. For dynamic viscosity, you could use something like a cone and plate rheometer. So you will put your sample in between a cone plate and a parallel plate. You will rotate one of those and you will measure with one of those the torque required for that rotation, and that will give you your shear stress to shear rate ratio or the viscosity. You could also use something like a falling ball type of viscometer, where the dynamics of a ball falling through a fluid will give you the resistance of that fluid to flow. Or you can use something like BROC technology, which is a microfluidic MEMS combination, a microfluidic based viscometer, which I will explain the principle of operation in a little bit more detail later. But basically, you're going to measure the pressure drop through a microfluidic channel, and that's going to give you your shear stress and your shear rate ratio. So you can connect those two with this very simple equation, just dividing by density. But in the case of kinematic viscosity or momentum diffusivity, we often measure, the property that we measure is actually time. So you often measure either the time or the volume dispensed on a given time. And these are examples of capillary tube viscometers, or just sort of cup type of viscometers. So there's many different times, and they often involve a calibration constant that will give you the kinematic viscosity based on a time or a volume that has been measured. All these flows are very often gravity-driven flows, and that's how we characterize that viscosity. So within shear viscosity measurement, even within dynamic viscosity measurement, we have different degrees of measurement, and that's very important because, as I mentioned, this is going to govern things like the pressure drop that you will have in a given system for your fluid. It will also determine what's the Reynolds number, so it will determine if you have flow instabilities or not. It will determine the flow rate and the shear rate. So this is a property that you really want to have a handle on if you are working with fluid systems. So the first, or I guess the less complete degree of measurement will be an index. So by this I mean that you will be able to measure sort of something proportional to your viscosity, and you will be able to compare sample A to sample B to sample C and establish which one of those is more viscous, which one is thicker. But you won't be able to compare those measurements to something measured with a completely different system. And this will be true only for Newtonian fluids. If you have non-Newtonian fluids often, you're not able to control shear rate, then you are not able to compare those samples. So application will be clearly something like QC control for Newtonian fluid viscosity. The next degree of measurement will be apparent viscosity, which is something that we often use to refer to the viscosity that is measured for Newtonian fluids, but that it doesn't necessarily correspond to the actual property. So if you cannot control shear rate, you often measure this apparent value, and then you will need to apply a correction or some kind of procedure to obtain the absolute or true viscosity at the shear rate, which is the next degree of measurement. Absolute viscosity or true viscosity that we often refer it to will be consistent for any fluid, and it will be consistent across different instruments. So if you are measuring, let's say, with a V-Rock chip or with a Conan plate or any other system that will allow you to control shear rate and measure viscosity as a function of shear rate, then you should obtain the same value and the same behavior for your samples. So of course the kind of applications will be characterization of non-Newtonian and Newtonian fluids, and it will be platform independent as I just mentioned. So here are listed a few of the applications that we have worked in the past, and I'm just going to go through them. Before I go ahead, I want to mention that we have pretty large application library that covers in more detail most of this, and we also have a pretty large webinar library that will cover in more detail some of these applications. So if you're interested in getting more information about any of those, I will recommend you to actually go there and look for the information, or send us an email and I will direct you to the right spot. So the first application that I want to discuss is injectability. So you will use shear viscosity to actually establish what's the force required to inject, let's say, a given formulation into a patient. And that's going to depend on the injection system that you're using and the needle that you're using, as well as the flow rate that you're using to inject that formulation if your formulation is non-Newtonian. So you will need to characterize the fluid that you're injecting at the shear rate that is relevant for that specific injection application. And that will allow you to calculate the force that you require to inject your sample or your formulation into the patient. The next one will be injetting. So if you are working with inks, for example, and you need to inject them into, to do some kind of printing, the droplet formation itself and the quality of the print are going to be affected by shear, extensional viscosities, as well as the surface tension and wetting properties. So shear viscosity is something that you want to have a handle on if you're doing injetting. Very similar for 3D printing. For some of the 3D printing methods, you will want to characterize what's the viscosity of the fluid at the specific temperature that you're printing to sort of determine what's the flow going to be like, and then qualify the quality of your prints. Some other applications such as stability, where you can measure viscosity as a function of temperature and changes in viscosity, or the structure of a formulation as a function of temperature, are also doable through measurements of shear viscosity, as well as measurements of solubility and saturation in different formulations. So I covered in the previous slide a little bit different methods to measure these different types of viscosity. So how do we measure it? So this is the sketch for bedrock technology. You can see that it's a microfluidic channel where you're going to be pumping a fluid at a non-flow rate. You know the dimensions of the channel, so that's going to give you from the flow rate the shear rate. And then because you have at the bottom of the microfluidic channel, you have an array of pressure sensors, you're going to be able to characterize the pressure as a function of position in the microfluidic channel. The pressure drop that you're measuring is going to be proportional to the shear stress, and the ratio of those two is the definition of viscosity. So we have a few products that are all powered by this technology. MVROC will be probably our most versatile R&D unit, Viscometer. Microvis is our small portable unit that is very good for on-site measurements or quality control purposes. And then last but not least, Recognition is our latest product release. Our previous webinar was about it. And it's powered by the same technology, but all the measurements are automated. So sample loading, measurement, and cleaning are automated. So you can test a large number of samples in a very with very little human interaction requirement. All right, so that's it for shear viscosity for now. So now we're going to cover extensional viscosity. And as you might imagine by now, extensional viscosity is the resistance of a fluid to extensional flow. So you can imagine this as being a piece of rubber or just a piece of fluid that you're putting between two clamps or two plates, and you want to stretch it. And then as you stretch it, you're going to be reducing sort of your cross-sectional area at the same time that you're extending your length. And that's going to define what's your stress ratio, what's your Henke strain, which is a measurement of the total extension of your fluid or sample. And then depending on how fast you're stretching the sample, that's going to define your strain rate, which is no more than the velocity that you're stretching it at divided by the original length. So with those, you are also going to measure the force required to stretch this fluid. So or the force, the resistance to this flow, extensional flow of your fluid, and that's going to give you your first normal stress, which is the force divided by the cross-sectional area. And very similar to shear viscosity, the ratio of the first normal stress to the strain rate is going to give you your extensional viscosity. So there is a good number of applications for extensional viscosity. The first one will be oil extraction and recovery. So very often for fracking, we use large molecular weight water-soluble polymers that facilitate the extraction of oil from different cracks. And you can imagine that in these flows, you're pumping at pretty high pressure, and you're having your fluid going through sort of sections of the cracks that have different changing cross-sectional areas. So the fluid is going to be getting stretched all the time. So knowing the extensional properties of these samples it's very important for this process. And here you can see some examples of a few different HPAM formulations in water or seawater, and you can see how actually these fluids are characteristic for having strain hardening. So as you stretch them at a higher strain rate, you're going to have higher extensional viscosities. The next example will be for injetting. So you can see here how as you're injecting ink through a nozzle, you're going to be sort of reducing the cross-sectional area, and that's going to be similar to, actually here you're going to have a combination of shear and extensional flow. But for some inks, it will be very important to know what's the actual extensional properties of your sample. Of course, the quality of the print is going to be affected not only by the two viscosities, but also by the surface tension and the wearing properties of your fluid. Here in the example, you can see very thick ink or a paint, if you want. It was a conductive ink. that is actually strain thinning. So as you increase the extensional rate, you get a very different behavior with respect to the previous sample. You get a decrease in the extensional viscosity. And in the insert, you can see what's the true tone ratio for the sample, which is the ratio of extensional to shear viscosity, which for a Newtonian fluid should be right around 4 in this case. And then finally, as I mentioned, for 3D printing, you have a very similar process, but in this case, you're printing a melt polymer with some of the 3D printed technologies. And then, of course, the viscosity of that melt is going to have a huge effect on how things are, what's the quality of the actual 3D print parts. Right, so there is a few ways of measuring extensional viscosity. The most simple one, it's very similar to the explanation that I just gave of what's extensional viscosity itself. You're just going to have two plates, you're going to place your sample in between, and you're going to stretch it. So that when you are working with fluids, makes you rely on adhesion of the fluid to the plates, and that limits very much what is the Henke strain that you can achieve without having a slip, and what is the strain rate, how fast you can stretch these samples without having a slip as well. Another way of doing extensional viscosity is rotating drums, but for this case you need a solid-like or a sample that is very solid-like, elastic-like. So you will have this sample, which will be something like polymer, melt, or a piece of rubber, and you will place it between these two rotating drums, and as they rotate, they will stretch your sample, and that measuring the torque that you require for that extension will give you your measurement of extensional viscosity. So now how do we measure it? So the idea is very simple, very similar to B-Rock technology. We call it EV-Rock, and we modify our microfluidic channel to have a constriction in the center. In this case, a hyperbolic shape constriction. So as you're pushing the fluid through, and it has to go through the constriction, it's basically going to get stretched. So now if you measure the pressure drop through the constriction, it's going to be proportional to the first normal stretch. And then by knowing the dimensions of your channel and the shape of the constriction, you establish what's the strain rate. And then by definition, you have your measurement of extensional viscosity. All right, finally, we are going to cover intrinsic viscosity, which is measured through measurements of shear viscosity, but it's a property on its own. And intrinsic viscosity, it's a measure of a solid's contribution to a given solution. So the idea is that you will add molecules of your solid to a given solution one by one, and you will track what is the increase or the effect on the viscosity. And that's going to give you a measurement of the strength of the interactions between the solid and the solvent molecules. So this will be the formal definition. So it's the limit when the concentration of your solid molecules go to zero of the relative increases of viscosity divided by that concentration. So it can be used for a number of applications, but I will say those are, it's very often used in polymer science to measure molecular weight using Marr-Hawkins-Sakurada expression. So you have a power law sort of expression that relates the molecular weight to the intrinsic viscosity measurement. If you have, for example, larger molecules, you will have a bigger effect on the viscosity, and you will get a larger viscosity, as you can see here. And that's also going to allow you to determine, once you know the molecular weight, what's the actual size of those molecules. So that's very often used to characterize the size of biopolymers or proteins in different solutions. So if you can imagine, if you change your buffer and you have, for example, different pH, the size of your protein is going to be different, and you can use intrinsic viscosity to determine those changes, and that will present it as a complementary technique to DLS for characterization of protein size. So it can be measured with a number of techniques, but the general idea of how it's measured is very simple. You're going to measure at a number of concentrations that are below some critical concentration threshold, where those solid molecules will be so populated that we will start interacting among them. So you want to be below that critical concentration. That is roughly below 1.5 times divided by intrinsic viscosity. And then you're going to measure several concentrations. Then you're going to measure the relative increases on viscosity, and you can either use Huggins or Kramer, or there's another number of relations that you can use to extrapolate to zero concentration and get your measurement of intrinsic viscosity. So the key here is that you need a very repeatable, very precise instrument to be able to establish those very small changes in viscosity as a function of concentration. So if you're using something like a rheometer, just the variation that you get just for your sample loading procedures from sample to sample or from concentration to concentration, that's going to affect your repeatability so much that you're not going to be able to track those changes in a way that allows you to measure this property accurately. So it's often used for this kind of measurements, capillary type of viscometers. That's how it's conventionally measured. It has a couple of disadvantages, or a few disadvantages. You need quite a bit of sample volume. It's very labor intensive because you have to clean your capillary tube in between each of the concentrations. So you can imagine that if you have to measure 4 or 5 concentrations for each of your samples to establish the intrinsic viscosity, you're going to have to use either 4 or 5 capillary tubes and clean them, or just use the one but successfully clean and measure the next sample. So that takes a lot of time. But you can actually do all these measurements with either of our instruments, and that reduces a lot at the time that you need to do these measurements. For one reason, cleaning is very straightforward. You can just flush some of the solvent in between different samples that you're measuring, but between different concentrations, you don't even need to flush. You just will use the next concentration to displace your previous sample, and then get your measurement, and then keep going. So you can get a set of data points with either of our instruments in a very, very quick succession. And we have the required high repeatability that is necessary for this measurement. So you're covered in that sense. All right, so with that, I would like to summarize. We have covered different types of viscosity, a few of the most common types of viscosity. Depending on the type of flow, we have covered shear and extensional viscosity. Depending on the type of measurement, we have covered dynamic, kinematic, absolute, apparent, and index viscosity. And then finally, intrinsic viscosity for molecular weight characterization and molecular size characterization. So I hope I have answered all the questions regarding what each of these types of viscosity are, what are their key applications, how they can be measured, and how do we actually measure it here at RheoSense. I would like to remind the audience that next week we have a very nice workshop here in South San Francisco. So you guys are still in time to sign up for this workshop and attend and get a sneak peek at the fantastic performance of our newest viscometer, with recognition. I will highly recommend to see it because it's actually a very nice product. And with that, I would like to thank you. and I will leave you guys with some of the specs for our viscometers. If you have any more questions about any of those, you can always contact us, and we'll get back to you. I will leave a couple of minutes for you guys to pose some questions, and then I will answer them quickly. Thank you.